Okay, you guys, today is more about interference. We're going to talk about interference that happens between two wave sources that are side by side. We're going to learn about what nodes and antinodes, what nodal lines and antinodal lines are. And then we're going to learn about the very heart and soul of constructive and destructive interference. And that's the concept of the path length difference. That is, you're going to learn it's not the distance that one wave travels, it's not the distance that the other wave travels, no siree, it's the difference between the distances that they travel. That determines whether they interfere constructively or destructively, and that's contained in this concept of path length difference. Alrighty, hey, let's get started. Suppose I have a single wave source. Here we go, just a second. Oh, microwave.
Sorry.
No, that's okay. Oh.
I forgot my food is in my gun.
At least I'm fire department compliant. Okay, here we go. So here it is, my single wave source. It might be that you drop a pebble in the water and then you create all these circular waves. Or maybe this is a speaker, a sound audio speaker, and it's putting out waves in all directions. But whatever, you've got some source putting out waves in all directions. Now, we need some way to draw the waves, and so we just draw it as concentric circles where every black line is a crest and every white line is a trough. So you picture this wave kind of going crest, trough, crest, trough, crest, trough, crest, trough, but I can't make a 3D picture, so I'm left with just black, white, black, white, black, white. You guys okay with that? So now, suppose I have a second wave source, let's say a second speaker, and this second speaker is playing the identically same tone as that first speaker. Well, if I put the two speakers right on top of each other, that is if the two speakers occupy the same place, then what kind of interference am I going to get here? Yeah, constructive. That is, a person standing here is going to hear a sound twice as loud as he would have heard had it been a single speaker, right? Two speakers, you get twice the volume. And you can see that because these two waves are meeting crest to crest, trough to trough. That's why you're able to see black and white and black and white. Because these two waves are meeting crest to crest, trough to trough. Crest to crest, trough to trough. Black, white, black, white. You guys okay with that? But what happens if I move one of the speakers? What if I move the speaker to the side? Can you see what's happening? Are you able to see, Zena? Is my big fat body in the way? You guys okay with that? Can you see what's happening when these two speakers are moved? Are you seeing those lines? You guys see it, right? Hope so. So, how about if these two speakers happen to be this distance away from each other? Then look at, let's say, this line here. Look at that line. Do you see the two waves are meeting crest to crest, trough to trough? I know they're meeting trough to trough because I can see the white, right? So everywhere along this line, the two waves are meeting crest to crest, trough to trough, crest to crest, trough to trough. So tell me, what kind of interference am I getting for anyone who's sitting along this line? Anyone who's sitting right here along this line is always going to get a certain type of interference as these waves move. What kind of interference are they experiencing? How many people say destructive interference? How many people say constructive? Yay, thank you. You're paying attention. Oh, that makes me so happy. Great. This is indeed a line of constructive interference. And because it's a line of constructive interference, it gets a special name. It's called an antinodal line. Antinodal line. It's called antinodal because a node or a nodal line is a place of minimal energy or minimal motion. But here you're getting maximum. You're getting maximum volume, maximum motion. It's constructive interference, maximum amplitude. But what about this line right here? And here, let me use a different color. What about this line right here? How are the two waves meeting along this line? Well, you'll notice it's always black. So are they meeting crest to trough, trough to crest, or are they meeting crest to crest, trough to trough? How must they be meeting if there's no white here? Thank you very much, Izina. I might have had to stay here all day waiting for an answer, but you answered. Yeah, you see they're meeting crest to trough. Crest to trough, trough to crest. So there's no white. It's all black. You guys okay with that? And so this line here, what kind of interference am I getting on this line? Hopefully you're thinking destructive if they're meeting crest to trough, trough to crest. So I'm getting destructive interference. Okay? And there's a name for this line where the waves are always meeting crest to trough and trough to crest. We call it a nodal line. So at this point, I would like to define what a node and an antinode are. We're going to encounter those terms a lot more in the next week, but I just want to define them now. Node is a point of minimal motion or energy. That's a node. An antinode is a point of maximal motion or energy. Well, what you see here, we can actually experience in real life. I have here, we have here my little system. Okay. I've got this speaker. I got this speaker. Okay. And I'm going to play an identical tone in each of those speakers. In fact, the tone I play will be a 5,000 hertz tone. And what will happen, just as what's happening here, you're going to find that if you move your head ever so slightly, don't just wag your head or you won't really experience it. If you move your head ever so slightly, you're going to find yourself at a nodal line. And you go, oh, that sounds a little quieter. And then if you move your head a little, you're going to suddenly say, oh, it sounds louder. I'm literally going to set up this sort of interference pattern with my two speakers. So here we go. Okay. That's, here, let me just, that's pretty loud. Okay. Interesting. This, what you're hearing now is about 460 hertz. Okay. What you see here is it's called an oscilloscope trace, and this is showing, this is a picture of the electrical signal that's going to the speakers, and that electrical signal vibrates the cone, and then you hear the sound, okay? I want you to see that as I raise the frequency, as I raise the pitch, what's going to happen to the wavelength? Should decrease, right? And do you see the wavelength decreasing as I raise the frequency, or the wavelength is increasing as I lower the frequency? You guys okay with that? And that's because the wave's traveling at the same speed no matter what the frequency or wavelengths are, so the wavelength and frequency are going to be inversely proportional. Okay, well let me get to 5,000 hertz. Okay. Okay, and now see if you experience it. No. No, you're right. That's what we should do. I don't know. Move it a little. Let's see if that happens. That would be freaky.
Okay, that's enough.
Good enough?
I hope.
Okay, so how many people here actually experienced something like this? Okay, good for you guys. How many people experienced where like it sounded loud in one ear but not the other? Yeah, exactly. You're experiencing this. Okay, so good. I just want you to see this is real life. Okay, let me turn off this obnoxious sound. Okay. I won't need this anymore, so I'll plug the microwave back in. So here's another example of that sort of thing. These are actually waves. You can see crest, trough, crest, trough, crest, trough, but these are flat waves, or you might think of them as plane waves. This is like the light waves that come from the sun, where when they first come from the sun, they're concentric circles, just like this drawing I showed you, but by the time these waves get to us, the circles are so gigantically big that any small little part of that circle is essentially a straight line. So you get waves that look like the waves that crash on the shore. It's just a straight line. But what if I had another straight line source of waves and they like interacted with each other? Well, I want you to see right now, do you see that these two waves, these plane waves, are interfering constructively, crest to crest, trough to trough? That's why you're able to see the white. If one was 180 degrees out of phase, if they were meeting crest to trough, trough to crest, then you get this sort of thing, you know? And if they're, you know, at an angle, then you start getting nodal and antinodal lines. You guys okay with that? Okay. So what I'd like to do is I'm actually going to let you guys pass this around so you get to play with it. Because the first time I discovered this, I had some fun playing with it. So I don't know if you guys want to do that. It's kind of interesting. Well, now it's time to talk about why you guys were hearing loud and soft. Why is it that these two tones were sometimes reinforcing each other and sometimes canceling each other? In order for you to understand that, you need to understand this concept of the path length difference. So let's go ahead and do that now. Path length difference. Okay. Imagine I have a speaker, and the speaker is putting out a particular tone and is going to some listener. Okay, this guy is hearing the tone from that speaker. And let's say I had another speaker, and that speaker was putting out an identical tone, and it was reaching that guy. And the two speakers are the same distance away from that guy. Tell me, what kind of interference is this guy experiencing right now, constructive or destructive? Hopefully you're getting constructive. DeAndre, why'd you say constructive?
Crest to crest, trough to trough.
Beautiful, crest to crest, trough to trough. It's that easy, right? Both of these waves are moving in that direction, so they will always meet crest to crest, trough to trough. So the amplitudes are reinforcing each other. Then I decide, you know what? I'm going to put this speaker on a dolly. And I'm going to be able to move this dolly back and forth along this horizontal line. Tell me, is there somewhere else I can put this speaker so that that dude would still experience constructive interference?
Like on the net.
Say again?
Like one exact wavelength.
Imani says 1 exact wavelength over. How many people agree with her? Darn straight, darn tootin'. You move this guy over 1 wavelength. Okay, here we go. And let me make my little dolly here. Okay, you move him 1 wavelength over. And yeah, you're going to get constructive interference. Okay? I want you to see what matters is not the distance between that guy and that guy, and what matters is not the distance between this guy and that guy. What matters is the difference of the distances. This wave is going 1 wavelength farther than this wave, and for that reason, they're meeting crest to crest, trough to trough. Is there another place I could put that speaker besides 1 wavelength over? Where? Anyone thinking 2 wavelengths over? Yeah, absolutely, right? I can put the guy here. Why not? There's no law against it right now.
Put it down.
Yeah, right? And so now my path length difference, that is the difference between the length that this guy travels and the length this guy travels, is 2 lambda. You see, again, it's the differences of the distances. It's the path length difference that I care about, not the different distances of the individual waves. And of course, it doesn't have to be 1 lambda or 2 lambda. What else could it be? 3 lambda or 4 lambda or 5 lambda, right? And it doesn't have to be to the right. Where else could it be?
To the left.
To the left. I could be 5 lambda away, 5 wavelengths away, and they'll still meet constructively. So what was happening with you guys when you were experiencing constructive interference is it just so happened that the wave coming from this speaker, let's say I'm looking at Fatima, the wave coming from this speaker had to travel a shorter distance to Fatima than the wave coming from this speaker. If she was hearing constructive interference, how much shorter of a distance? Either lambda or 2 lambda or 3 lambda or 4 lambda. It had to have been a multiple of lambda if she's hearing constructive interference and this guy's traveling farther than this guy. Then the distance, the farther he had to travel than this, had to be a multiple of lambda. You guys okay with that? Okay, so let's go ahead and I'd like to define path length difference. Path length difference. And path length difference is the difference between the distances that 2 waves must travel to get to a certain point. What's that? Oh. The difference in the distances 2 waves travel to get to a certain point. Like that dude. Okay. Path length difference. That is the end all and be all. It's the sine qua non of understanding constructive and destructive interference. Yes. Yes, I can answer that question. Yes. So, for constructive interference, you tell me the path length difference, and by the way, I'm going to abbreviate path length difference as PLD, but I'll keep saying the words path length difference. I'm not going to say PLD, but I don't want to write path length difference every time. What must the path length difference between 2 waves be in order for them to interfere with each other constructively? What should I write? Oh, please. Someone answer. I'm going to call on Noel. Yes, Cole. Were you going to say something? No. Yes, Logan. Thank you. 1 wavelength. Beautiful. Is there another wavelength that'll get me constructive interference besides 1? 2 wavelengths. Good. Is there another one? Yeah. Dot, dot, dot.
Solid numbers.
And so yeah, solid number, we'll call that an integer. And so we end up using path length differences n lambda, where n equals an integer. You guys okay with that? That's my formula for constructive interference, n lambda, where n equals an integer. But suppose I don't want constructive interference. Suppose I'm the type of person who likes to destroy things. Maybe I'm that guy. Anarchy, baby. Maybe I want destructive interference. Well, I got the same speaker. That speaker is traveling along that same horizontal line. You tell me, where should my other speaker go so that I get destructive interference?
Anywhere in the middle of a wavelength?
Say that again?
Anywhere that's not a whole wavelength?
Okay, Imani says anywhere that's not a whole wavelength or and somewhere in the middle. Well, what she says could get me varying degrees of constructive or destructive interference. That is, I could be combining the waves and the resulting amplitude could be bigger than either of the original ones or smaller. But what if I want complete destruction? Yes, Sean?
Oh, no.
Oh, okay, what if I want utter complete destruction? Because that's just the guy I am. Yes, Logan, where should I put my speaker?
A half wavelength though?
How many, was that what you thinking, Noel? Is that what you thinking, Alejandro? Yeah, you guys okay with that? Half wavelength, precisely. If I'm precisely a half wavelength, now my speaker begins its, my speaker begins its, what do you call, wave right here. And you know, remember I'm still on that dolly with the wheels. But I'm going to begin my wave right there so that I go crest, trough, crest, trough, crest, trough. You guys okay with that? I'm now getting destructive interference because these waves are combining crest to trough, trough to crest. And this distance from here to here is 1/2 of a wavelength. Beautiful. Now here comes the hard part. Where else could I put that speaker besides 1/2 wavelength to the right of the original speaker? Yes, Alejandro?
1.5 wavelength.
How many people agree with them 1.5 wavelengths? Yeah, 1 wavelength over beyond this. Now that I've got destructive interference, I'm just going to move him over so that he keeps having the same type of wave. You know what I mean? Again, I'm going to have destructive interference, and this distance from there to there is 1 entire wavelength. Okay? So let's go ahead and summarize what we've got. For destructive interference, I need my path length difference to equal 1/2 lambda. Or, do you mind if I call this distance here 3/2 lambda? Or 1.5 lambda? Tell me, what's the next one after 3/2 lambda? Yeah, 5/2 lambda. That is lambda more. You know, another lambda will still get me destructive interference. So 5/2 lambda, etc. And so now I'm going to get an equation. And this is something that's going to require a little bit of math. Who here can tell me what equation where n is an integer, what equation is going to get me the path length? What must the path length difference be equal to get me destructive interference? Yes, Giancarlo?
N plus 2 over 2.
Okay, beautiful. N plus 2 over 2. You guys okay with that? N plus 2 over 2. But instead of writing it n plus 2 over 2, do you mind if I split the fraction and call it n over 2 plus 1? Okay, so that's what I'm going to call it. This is going to be Just a second. Yeah. I'm sorry, I'm just, n over 2 plus 1 lambda? Although, how do I express it in my notes? Wait, is that correct? Yeah. 1, 2, 3. No, that's not gonna, is that gonna get me there?
Yes, we will.
No, it's not gonna get me there. No, that won't get me there. Because if n is 2, I get 2 lambda, and 2 lambda is constructive. So that's not gonna get me there.
I'm writing
That was a
it.
good guess, but if n is 2, that's no good. Okay, 2n plus 1 over 2. What are you saying, Alejandro?
And over to the
N plus 1/2.
Yeah, I'm gonna go with that, but that's the same as you. What did you say again?
2n plus 1 over 2.
2n, wait, 2n plus 1 over 2, which is n plus 1/2.
Yeah.
Okay. Now, Giancarlo, was I misunderstanding you? Was this what you were telling me? Okay, well, I'm gonna go with this. N plus 1/2 times lambda. But more often than not, you're gonna be called upon to just know that it's half lambda, 3 halves lambda, 5 halves lambda, ... That's what you're gonna have to know. Well, hey guys, it is now time to do some problems involving those formulas. Here we go. I got 2 speakers and 1 dude listening. The distance between this speaker and the dude is 3 meters. The distance between these 2 speakers is 4 meters. Both speakers are giving out sound that he's hearing. Identical tone. My first question to you is this. What's the path length difference between those 2 sounds? What's the path length difference between the sound he hears from this speaker and the sound he hears from this speaker? Good luck. Okay, I'll give you 2 choices for the path length difference. It's either 2 meters or 1 meter. Are you ready? How many people here say the path length difference is 2 meters? How many people say it's 1 meter? Wait, almost no one raised their hand. Remember, the path length difference is not the distance between here and here. It's not the distance between here and here, no siree. It is the difference between the distances, right? So please, I'll give you 20 more seconds to get the path length difference. Okay. How many people say the path length difference is 2 meters? Yay, thank you so much. Beautiful. Good. Because this distance from here to here is 5 meters, and the difference between 5 and 3 is 2. The path length difference is 2 meters. Okay, so now I'm going to do a problem, then I'm going to have you guys do a problem. Here's the problem I'm going to do. Find the 2 lowest frequencies that give constructive interference. what are the two lowest frequencies that those speakers can be putting out such that when those two waves reach this guy, you get constructive interference? Well, if I'm asking for frequency, and all I've got is an equation for wavelength, there's only one equation I have that relates frequency and wavelength, correct? And that's V equals F lambda. So whenever they ask you a question about frequency where path length difference is involved, you know you're going to use that formula. At this point, I need to tell you that the speed of sound, we're going to say the speed of sound, which is the speed of the waves that the speakers are putting out, is approximately 340 meters per second. So there you go. I get to say 340 for V. Now, I need to find an expression for lambda. And the only equation I have that relates this sort of scenario with path length difference and wavelength is this guy right here. And it's constructive I want. So I need my path length difference to equal n lambda. Well, I want the two lowest frequencies, so that means I want the two lowest wavelengths. So I hope you see that I'm going to have to let my path length difference equal lambda, and I'm going to have to let my path length difference equal 2 lambda. That's going to get me my two lowest frequencies. If they wanted the 3 lowest frequencies, then I'd have to let path length difference equals lambda, 2 lambda, and 3 lambda. But they only want the 2 lowest frequencies, so I'm just dealing with lambda and 2 lambda. Well, my path length difference is 2 meters. So a wavelength of 2 meters is going to get me constructive interference. So let's go ahead and put that in, 2 meters. And so I end up with 170 hertz equals the lowest frequency. But I'm also going to get constructive interference when my path length difference is equal to 2 lambda. That is, my path length difference, which is 2 meters, has to equal 2 lambda, which means 1 meter equals lambda. If I wanted to compare what's happening, let's say I'm here, okay? Or let's say just a second. Okay. Okay. This guy here, saying my path length difference is equal to lambda, would be like saying, hey, the distance between here and here is 2 meters. That's my path length difference, right? 2 meters. Having the path length difference be just lambda would be this. It would be like, okay, I'm going to go like this, then I'm going to catch my wave, and it's all good. But the path length difference equaling 2 wavelengths means I would have something like this. I'd have to say, okay, this guy is putting out the wavelength has now been cut in half for both of those tones. So this guy, instead of looking like that, this guy's going to look like this. Okay. And this guy's going to look like this. You see? And now they're catching each other crest to crest and trough to trough, but I cut both of their frequencies in half. I cut both of their wavelengths in half, which means I doubled their frequencies. So now this same 2 meters, instead of being a path length difference of 1 lambda, has become a path length difference of 2 lambda. 2 wavelengths. I'm hoping that's making sense to you guys, because that's what's happening. So anyway, so now I'm going to do V equals F lambda. So I got 340 meters per second equals F times 1 meter because that's what the wavelength is now. And so I get 340 hertz. So those are the two frequencies that I'm going to get constructive interference on, 170 and 340. 170 is like the blue wave, and 340 is like the red wave. 340, I got a path length difference of 2 lambda. The 170, I got a path length difference of 1. Any question or problem on that before I have you guys do one on your own? Okay, then here comes number 3. Get the 2 minimum frequencies for destructive interference. Okay, good luck, you guys. Good luck. You're going to do it the same way, only which formula are you going to use now? Thank you very much, Imani. The n equal blah, 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 the other one. Yes. Good luck, you guys. What time is this crazy class over?
37.
Oh my God, 37? Okay, well, I'll give you a couple minutes to do it, then I'll show you the answer. If you're stuck, you should be using your path length difference, which is 2 meters, by the way. That hasn't changed. You should be using your path length difference as 1/2 lambda, path length difference is 3/2 lambda, in order to find what lambda is. And then you just plug that into this equation, v equals f lambda. So keep going. When you're done, look up. You should be getting 85 and 255. And your lambdas, one lambda should be 4 meters and the other one should be 4/3 meters. Any question or problem on this? All right, well then, hey, the last thing I got to tell you is tonight's homework problem number 8. They tell you that the 2 speakers are 180 degrees out of phase. That is, the 2 speakers, one guy starts off crest, trough, but the other speaker goes trough, crest, crest. You see, they're 180 degrees out of phase. That is, one's inverted compared to the other. So tell me, if I want destructive interference, now which of these two equations am I going to use if they already start off inverted? Yes, go.
Constructive.
Beautiful, thank you. That's it. If you want destructive interference, use the constructive equation. Good luck.